Hello, welcome to session number 14 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in the last session I was talking about Butterworth or maximally flat filter, and in that case I have uh, shown how to implement a Butterworth filter using normalized circuit components obtained from the approximation of a Butterworth polynomial. Now what I'm going to show you is same treatment for Chebyshev, and for that treatment, right, it's just that the coefficients are going to change, right? So let's say I'm going to design for a ripple of zero point 0.1, right, and I'm expecting a 30 dB, okay, at twice the frequency, which means that W by or omega by omega c minus 1 is going to be 1, right? So at this point I'm expecting a better than 30 dB of rejection. So that shows that the order of the filter is 7, right? So this pink line has to be uh, above the marker, right? Okay, so at this marker the attenuation is going to be 35 dB. So let's see if we can do the same treatment uh, with the Chebyshev polynomial. Now, last time I showed you a MATLAB code and I was deriving the coefficients. So right now, okay, I want the coefficients for 0 0.1 dB ripple, correct? And I want the fifth order, and these are my coefficient values, right? 1.1468 and 1.3712 and 1.9750, 1.3712, 1.1468. So these are my coefficients. Now let us look at Mathey, Young and Jones, whether they have the same coefficients. So let me see. Okay, so let me open Mathey, Young and Jones. Yeah, so let's focus on 0.1. So we are looking at 0.1 dB ripple, am I? Yeah, 0.1 dB ripple. So the table which I'm going to use is the second table. And fifth is 1.1468, 1.313712, 1.7, 1.9750, 1.3712, 1.1468, and then 1. So basically my function which I have written in MATLAB to compute these is correct. Okay, maybe I was looking at a wrong table last time in the last session, but this algorithm I verified for 0.1 dB, 0.01 dB, zero point 0.1 dB, 0.2 dB, 0.5 dB, and I found that this algorithm is okay. So let's go ahead and do that. So to do that, it's very simple. You go to your LPF Butterworth. Now this LPF Butterworth, you see, has everything in it. Okay, it has got LPF, it has got HPF, it has got BPF, and it has got BSF. All I need to do is just change these coefficients, isn't it? And all these things will be designed automatically, right? So this template, I can just change these coefficient values, right? So this is just to do with the pole placements, right? So there are 5 coefficients here. So I'll replace them. 1.1468, correct? And then next one is going to be 1.3712. The next one is going to be 1.9750. The next one is going to be 1.3712, right? And the last one will be 1.1468. So just make sure that these coefficients are rightly typed, right? So to me it looks like fine. So we are ready with our, oh, I shouldn't have done it here. Let's undo this. No, let's redo this. Let me just copy this, Control C, and let's undo this. So this is a Butterworth, I don't want to disturb that. I'll just copy the cell, copy cell, and I'll call it as TCHEBYS. Maybe my spelling is wrong. Okay, Chebyshev. And then I will open this one and alter this one. So to alter this one, I have to just throw this one out and say Control V. So this is my Chebyshev coefficients, and I have to just hit simulate. So once I have done with simulation, I am going to look at S21, which is a low pass filter. S21 is a low pass filter, Chebyshev. Add in dB. So this is a Chebyshev low pass filter, and if I zoom in, I would be able to see that. But what I want to do is I want to overlay this on top of the polynomial itself, right? So what I'll do is I'll go in here and go to LPF Chebyshev, and here I will look at S21. Okay, so there you go, that's S21, and say add versus in dB. I'll go to the frequency. So let's see, where is the frequency? At the top maybe. C, D, E, F. So somewhere here it should be frequency. Okay, so now what I want to do is I want to normalize this frequency to 12 gigahertz. 12 gigahertz, and then subtract 1 from it, right? And you will see that again this is on top of that. So let me just change the color to be green, and let's do a dotted line. Okay, so what does it look like? It looks like that the polynomial and its fifth order approximation, they are almost the same, right? So that means so that the green one is coming from this circuit simulation for Chebyshev, isn't it? And that red one is coming from the equation. This is the equation for a Chebyshev polynomial, right? So that being said, let me also see whether ripples are correct. So I'm going to go ahead and plot here also. I'll go to S21. Sorry. In this case, this is called, what was it called? LPF. LM. Okay, LPS Chebyshev. I want to look at S21. So S21 add. No, sorry, S21 add versus. Okay, and I want to do frequency DEF frequency, and then I'm going to normalize this expression frequency divided by 12 gigahertz minus 1. Okay, say okay. So you will see again I will make it dotted. Sorry, trace option dot. So you will see again that the ripple also matches the polynomial. So that's blue one is from the circuit simulation, and the red one is from the polynomial. So basically it just matches whatever I want to, whatever my equation is. So I'm sure that my algorithm is correct, right? So now let's look at a few more things. Now I have verified this, that Chebyshev is working properly. Close this. Now what I want to do is over here I want to put what you call delay. Okay, group delay S21. Sometimes while speaking I might do some slip of tongue and I might wrongly define it, right? Its units are time, right? So if you have theta, d theta by df, okay, the units would be time. So that would be called a group delay. Okay, d theta by df. So earlier I might have a slip of tongue, right? So please don't mind that. Okay, so I'll put this on the right hand side axis. Right, and now you see that it's kind of more stable, isn't it? It's kind of more flat, right? It's kind of more flat compared to what Butterworth was doing, right? Now, as you keep increasing the order, this is going to become more and more flat, right? So this is suitable for your pass band characteristics you are desiring. Otherwise, you might have to do an all pass phase equalizer. which I'm not talking here, but in communication system, if you want to make the phase also flat, you might have to do an all pass filter, which is basically adjusting the phase equalization. So I'm not going to cover that in here. Okay, so that's that. Now I can do the same thing for the, so that will be 4-3. This will be high pass approximation, high pass transformation, and this would be, so why would I plot it even? Okay, I would not even plot it. I will just copy from the previous one. So I'll go here to its display, Butterworth display, and I'll just take this. Sorry. So I have selected all of it. I'll say Control C, and just I'll place it. Control V. Okay, there you go. There you have it. So it's just that here units may be wrong. Here I might have a y-axis right. Okay, so let's do this as 2. Okay, so now this looks okay. And why there is an additional this stop? There's some glitch in here. This should not be there. Should be a flat with this. Anyways, so there is something with the band stop transformation. Band stop transformation where I'm messing it up. Okay, anyways. So all these, low pass to high pass, low pass to band pass, and low pass to uh, band stop. All these transformations are done, right? And as far as the ripple is concerned, let's zoom into a band pass. Okay, so this has to be a 0.1 dB ripple, and it's slightly moved. Okay, but this is what a Chebyshev design would be, right? Okay, so after this I'm going to do an elliptic filter. So for elliptic filter I would have a table which would be slightly different, because in that case there are more components in an elliptic filter. So this Mathai, Young and Jones stops at Chebyshev. It doesn't do a treatment to elliptic filter. So over here, this is a very important book. So even if you do a LTCC design, for example, where there are all transformations are there. So this is mainly waveguides, right? But there would be sections like, for example, broadside coupling of these lines, right? That section you need to study well. Okay, once you study that section, you will be able to design. So there is a section here which you will be able to design filters on LTCC substrate. So right now this is numerical. So for example here, right, you have this equivalent circuits, right? So you should understand what this equivalence is. And once you know these equivalences, you should be able to do your band pass filters easily, right? There is no issue with the band low pass or high pass. The issue is with when there are resonant structures. So when there are resonant structures, you are supposed to do the structures properly, otherwise the response moves, right? So let me show you that example of broadside coupling. So this is quarter wave implementation. So let's show you broadside coupling. Okay, strip line and semi-lumped filter elements, something like this broadside coupling. So this is Chebyshev implementation of that. So let me show you a bandpass filter, and then you can use these resonators also. For example, this is what I was talking about. Now this is something which you can compute, okay? But then application engineer would do what? He would put this structure, he will specify all these as variables, and then what he's going to do, he's going to put an optimizer on it and a goal. But are you a designer? No, you would have optimized it for hours blindly, and when you fabricate it, if something goes wrong, you do not have a way to establish what went wrong. But when you design with the formula, you would know what went wrong, right? So that's the difference between, just passing the buck as an application engineer versus being a designer. Okay, so let's go ahead. So this is a very valuable book. Okay, so this is the implementation. This is a very valuable book, and this is out of print, but you might find a copy online. Okay, so this doesn't do Chebyshev treatment. So now I will do a Chebyshev design. Oh, sorry, elliptic design. Okay, so this is up to here. Unless I messed up something, the bend stop also comes out right. I messed up something on writing these formulas, right? So you can correct those. Let's look at an elliptic filter. An elliptic filter would have these ripples in the pass band as well as the stop band. That's what an elliptic filter is going to be like. And its basic structure for capacitor first is this. And the basic structure for inductor first is this. Okay, in some cases you are dealing with, in the first case you are dealing with anti-resonant circuits here. And the second case you are dealing with series resonant circuits on the shunt branches, right? So this is a table, okay, and here, okay, let me assure you this. You do this, okay, as if you find out, what you do is you find out what is the attenuation. So there is a attenuation at the stop band, and that stop band is omega naught, omega infinity. Omega infinity divided by omega corner. Okay, that is this ratio. And for every order, this ratio is there. And then you have got attenuation in this column. So let's say if I want to design a fifth order filter, right? And I want attenuation at omega infinity to be 30. So then I would be picking up this column. And if you would see, there would be 1, 2, 2 dash, 3, 4, 4 dash, and 5. So they are referring to 1, 2, 2 dash, 3, 4, 4 dash, 5. So you understood what that is, right? So I have this 1.25 is basically the stop band frequency divided by the corner frequency. Okay, so if the corner is 12 gigahertz, right? So 1/4 of 12 is 3 gigahertz. So 12 plus 3, 15. So at 15 gigahertz, you want a 31 dB of isolation, right? So you will implement this filter. So this will give you a low pass filter. So I'm going to design this filter, and I will keep it always odd. And this is for a ripple of 0.1 dB on the pass band, right? So that's the table for. Now you can find the same approximation table. Okay, you can find similar approximation table for different ripples. And the book to refer to would be, let me show you. The book to refer to would be this one, Handbook of Tables for Elliptic Function Filters. Okay, if you find, you can find this online. Okay, and this would give you approximation of elliptic. So it will give you for every omega s as a normalized to omega c. So it will give you all the tables, okay, for elliptic filter, right? Another book to refer to if you want, some kind of a formulae, right? So the another book to refer to would be Analog Electronic Filters Theory, Design and Synthesis, okay, by this author. In this you will find the treatment of elliptic filter. This is not going to be there in Mathai, Young and Jones, right? So that being covered, let's go ahead and design that. So what you're going to do is, I am going to create a new schematic, and I will call this as I'm calling everything as LPF, but inside LPF there is all the transformations also there, right? So I will say LPF underscore and underscore elliptic, correct? And say create schematic. Okay, so I'm going to copy some of the uh, parameters from the uh, butterboard, right? So some variables I'll copy. So these variables are going to be this one and this one. Okay, so this is for bandpass. This is for low pass. So I'm just going to copy this, Control C, and rest I don't want. Control V. Okay, so I'm looking at Fc is equal to 12 gigahertz, F0 is 10 gigahertz, F2 is 11 gigahertz for bandpass, and F1 is 9 gigahertz for bandpass, and impedance is 50 ohm. So similarly, you have got omega C, omega 1, omega 2, omega 0, right? Rest of the equations I'm going to write again, right? So let's go ahead, and these values, okay, these equations are going to be same, okay, only that CD2, right, there will be a slight variation, right? So just follow this. Let me just zoom in. Just follow writing these equations, okay, and then you place the components in and do that, CD1 to CD3, CD5. Okay, so let me just write these equations. Okay, so I am going to delete everything except delta, right? So CSH1 is CD1, which is G1 by Z0 omega C. That's correct. CSH3 will be the same. CSH5 will be the same. LS2 or LD2 is G2 Z0 by omega C. That's the same. Then LS4 is G4 Z0 by omega C. That's also correct. Now you will have to do CS2D or CD2D, isn't it? CD2D. Is there CD2D? G2D. Okay, so CD2 is that. Okay, so it will be the same thing, right? So it will be the same thing. So for example, I can do this as CS2D. Okay, CS2D, right? So CS2D is equal to G2D. Okay, G2D and add, and CS4D would be equal to G4D and add. So you are done with these equations. Only thing is you have to put in here the coefficients. So I am going to go here and insert a new variable, and I'm going to write all the coefficients here. G1. Okay, so let's look at my presentation here. Okay, so this is a fifth order, right? So we were picking so this is sixth, this is fifth order. We were picking this one. Okay, so 15 gigahertz is where this thing is, right? Okay, so 15 gigahertz, I want to see 31.49. So this is 0.9448, 1.106. So let me put this to the side. And so this is the one which I want to do. 0.9448, 0.9448, apply. Then you have got 0.9448 Then you have got 1.106. G2 is 1.106. Right. Then G2D is, okay, so the next one is G2D. So, okay. So this is G2 and this is G2D is 0.2694. 0.2694. 0.2694. This is G2D. Then you have got G3 and that G3, so I'll hit apply. So G2D, so apply and then G3. So G3 happens to be 1.4415, isn't 1.4415. This is what we are talking about. 1.4415. Okay, that is G2D. G3, sorry. And then you have G4. G4 is 0.6829. 0.6829, is it? 6829. And then you have G4D. D stands for dash, right? 0.8827. 8827. And add. And then you have got G5. G5 is going to be 0.604. 604. And one thing you should know about elliptic filter, it is not designed for exact 50 ohm. It is designed to tolerate certain VSWR. Okay, so it will not be matched to 50 on both sides. So you have G1, G2, G2D, G3, G4, G4D, G5. So let me just verify this. 0.9448, 1.06, 2.2694, 1.4415, 0.6829, 0.8827, 0.0604. Say hit OK. So we are all set. And this is going to be our elliptic filter. Okay, so let's quickly put those there, and I will rather copy it from LPF. So NPF, this is the circuit, right? And maybe I'll copy this also. Control C, Control V. And so you have got LS2, CS2, and CSH1, CSH3, CSH5, and all you need is capacitors. So that's one capacitor you need here, and another capacitor would be here. So in this case, this will be CS4D, CS2D. So this will be CS2D, and this will be CS4D, right? And I think I'm all set for the elliptic low pass filter design. Yeah, so I have an S parameter simulation here, and we'll hit simulate. Oh, LS4, CS4 to be output in an expression. Okay, so I copied this, right? So in this I had all this, right? So I am going to delete all this. So I'm going to remove. Oh, maybe it'll do only one time, right? So it'll already taken off those. Okay, so let's look at S21 response in dB. So that's your elliptic low pass filter, right? Makes sense. And let's do a delay on this one. S21. sorry, S21 delay. So delay is here, and let's put this on the right hand side axis. Okay, so now you see it is more flat. Then it shoots up. It shoots up more, but it's more flat. Okay, and if you zoom in, you will find the ripple here. That will be a 0.1 dB ripple here. And then if you check over here at 15 gigahertz, you are going to get better than 35. At 15 it is 33. So we are almost there. Now in this Chebyshev implementation, the book I referred, okay, you can derive different formulas. In one formula you can optimize for this cutoff. In one formula you can optimize for the stop band. In one formula you can optimize for the ripple. So refer to that book to be able to do that. Okay, so this is a low pass. I will do a transformation to high pass. Okay, so I'll do a transformation to high pass. Now refer to my this transformation. Sorry, transformation is going to be same. It's the formulas are going to be same. So if you see here, I have put these. Okay, okay. So this is basically I have written in terms of G1, G2, D. Okay, so I can write these again, not a difficult stuff, right? I'll just write this again and get a high pass response. Okay, so let's just do that. So this transformation is directly as in terms of G1, G2. Okay, so let's go to here, and here I'm going to put another variable var. Okay, so this is a high pass, so I will add a subscript h, right? So I am dealing with omega c is already there, right? I'm dealing with cs, and this is going to be h, again csh. That will clash. So what should I do? Okay, so I will do cs. I don't want to add more words. So let's say I add a substrate 1. Okay, cs1 and then 1. Okay, so cs11 is equal to 1 divided by something, which is z0 times of omega c times of g1, right? So apply that. CSS1 and then CSS3 will be the same equation, right? CSS13, CS13 will be G3. Say add, and then you will have this as 5, right? So in this case I would have CS15 will be G5. Let's say add. Then I would have LSH12, LSH12. So this is a shunt element, LSH, and then 1 stands for high pass transformation, and 2 is the second component, which is going to be equal to R0 by omega c G2. So that will be Z0 by omega c G2. So add that, and then LS. So this is going to be 4. 1 4 is going to be G4. Correct? Right. And then you have got CD2. This is the same formula. So add. And then you have got CSH. CSH1, 2. And that would be G2D. Isn't it? G2D. Okay. add, and then you have got CSH4, CSH, so you can just use this CSH4, and that will be G4D, 4D, and add. So I have all the components now for a high pass filter. Okay, so I'm going to place them over here. So all I need is over here 1, 2, and 3, 2 and 3, and these are going to be CS11 1315, CS11 13 and 15, correct? And then you are going to have shunt elements, so I'm going to repeat these. Okay, and this will be CSH1 2, and this will be CSH1 4, 1 4. Is that correct? CSH1 2 1 4, and then you have LSH1 2 1 4, LSH1 2 1 4. Okay, LSH1 2, and I'll just copy this 1 4, 1 4, correct? So now you are going to do this and put here terminal 3 and 4. So this is going to be elliptic high pass. So I'm going to hit assimilate. Warning, okay, no DC path, because this node will not find, these nodes will not find a path to DC because they are capacitors here, so it will always give you a warning like that. Okay, because it has to find a DC solution before it does a S parameter, right? So this will be 4 comma 3, and this will be 4 comma 3. So this looks like a high pass, isn't it? And this is going to be better than 30. So this is a elliptic high pass filter, right? So this is elliptic high pass filter. Why does it look? Yeah, that's okay. Now I have to convert this to a bandpass filter, right? And what would a bandpass look like? Let me show you. So that's the bandpass filter, right? And you have to write few more equations, but more or less they're going to be same, right? Or similar, so it will not be take you much time. So let's write those equations for bandpass filter. And band stop filter I'm going to leave as an exercise. What's going to happen is that this element which you see here as a series shunt will come in the shunt here, and what you see as a shunt will go in series here, so it will become a band stop filter. But that transformation I'm going to leave it to you. I'm just going to show you up to bandpass, so I am not interested in this one. Okay, I'm going to show you up to a bandpass filter. Okay, so all these are correct. Only thing which I need is there are 2 more elements on top of it, right? There'll be 2 more elements on top of it, and this would be your bandpass filter. So let's go ahead and write the equations for this, and I am going to copy same equations. Okay, so which one I'm changing? Oh, I did a mistake. I don't want to change this one. Okay, let's look at what you is working on. This one, right? So I'm going to copy these equations. Control C, Control V. and here I'm going to write CSH1 LSH1. Okay, so they are going to clash, right? So I'm going to look at CSH1, so I will rather do this as CSH2 and 2 1, right? CSH2 1 is equal to CD1, right? So this is G1 by omega delta R naught. Okay, so let me write it down. So rather I'll just delete all of them. Cut. Okay, so this one would be equal to, I have already computed delta, right? So G1 divided by omega delta, so it will be delta omega C. Instead you will have omega naught R0, omega naught. Okay, so it will be G1 divided by delta omega naught Z0. Correct? Apply. Now to make sure that this is correct, I'll just run a simulation once, unless it comes up with a warning. It did. What's the warning? Why would there be a problem here? Hang on. Okay, there is no problem. So now if I insert another variable, insert, so I'll say undo. So what went wrong with this? var6 CSH, it may be a repetition, right? CSH21 is G1 by this, so this is okay unless the name was repeating, right? So that's fine. Okay, so now very quickly, so this is CSH21, CSH23. So CSH23 will be equal to G3. CSH25 will be G5. Then you will have LSH21. This is the shunt element, which is delta R0 by omega naught G1. Delta R0 by omega naught G1. Omega naught G1. Delta R0. Delta into Z0. Correct? Delta into Z0 by omega naught G1. Right? And that I will say add, and then this will be 3. It will be G3. Add, and then there will be 5, and this will be G5. Add. Okay, so we are done with this, and then you will have LS2 2. So I'll do LS22. Okay, so LS22 would be equal to G2R0 by omega naught delta. G2R0 by omega naught delta. Okay, and I'm going to add that LS22. Then LS24 would be G4 R0 by omega naught delta. That's being done, and then I will have CS22, and that CS22 will be delta by omega naught R naught G2, delta by omega naught R2 G2, delta by omega naught Z0 into G2, right? So this will be CS22. Then you have CS24. CS24 will be delta divided by omega naught Z naught G4, and say add. Okay, so now we are done with the series elements. Now the shunt element here. Okay, so this one I will call it as CS D, CSD22, right? CSD22, C2D2. It will be G2D. Okay, it will be G2D. By the way, I didn't get it from a book. I basically just used the scaling from the table, which is given by in David M. Poshar. There is a chart for transformation given there. Omega naught R0 delta, V naught 0 delta. Okay, CSD22 add, and then you will have CDSD24. That will be G4D add, and then you will have LSD22, and that LSD22 would be R0 delta by omega naught G2D. R0 delta by omega naught G2D, and LSD24 will be G4D, isn't it? And so now we are done with all the equations for a elliptic bandpass filter, and I am going to just create the structure. So to create the structure, I'll go to the Butterworth. That's the Butterworth, isn't it? So I'll copy this thing. So I'll just copy this this one, right? This looks more familiar. Okay, edit, copy, cancel, edit, paste. Okay, so just follow the convention. CSH21 2325, CSH21, CSH23, and CSH25. Correct. And then you will have LSH21, LSH23, and LSH25. Right. So this is covered. Then you have LS22 and CS22. So this is going to be CS22. This is going to be LS22. CS44, sorry, 24, and LS24. So that being covered, CS24, LS24. Then you have CSD22 and CSD24. Okay, so I'll just copy this one. Okay, so CSD 22, isn't it? CSD22, correct, and CSD24. Correct. And then I'm going to move entire thing down a little because I need to adjust an inductor in there, and that inductor I'll just copy this one and give it a value. So this value will be LSD22, LSD22, and LSD24. So this will be LSD24. Okay, so I'm all set with the elliptic bandpass filter after this transformation, and this component will come in shunt with this series resonance circuit. And you will not find this in the books because the books stop at Chebyshev. right? Even Pochard would stop at Chebyshev. Okay, so this is my elliptic bandpass filter. So I'm ready for simulations. Oh, there is a problem, is it? Uh, Warning, DC path to ground. This is referring to what location would have a DC path to ground issue? Just 1 second. Let me see. The virtual resistance of 1 tera ohm. That's understood. That's okay. What's happening is that if you put here resistance to have some losses, okay, then this would go away. These warnings will go away. So let's look at 6.5. Okay, I simulated it for a long duration. Doesn't matter. So I will go from this is around this, right? So I'll go from 8 or 7 to 13, right? So I will go from 7 gigahertz to 13 gigahertz in steps of 1 gigahertz. Okay, and then I'll go from minus 100 to 10, minus 100 to 10, right? So I'll go from minus 100. This is for the DC point that you are seeing this to 10 and steps of 20. So rather make this as 20 and say okay. So this looks like your bandpass filter, or if you want you can even bring it down to 80 or let's say 90, and this will be 10. Okay, so this is your design, which is a 30 dB rejection wherever you wanted it to be, right? And let's plot here delay 6.5, delay 6.5, and put it on the right hand side axis. And this is your group delay. Okay, so this is your this is your elliptic filter design, and you can see the ripple is going to be 0.1 dB, right? So that's your filter. And band stop I will leave as an exercise for the audience. Okay, so you have a low pass, high pass, and band pass. If you want to do band stop, you will have a rare occasions where you want to suppress something. You might need a sharp cutoff band stop. In that case, you might use this elliptic band stop version of it. So I am going to stop here, and yeah, thanks a lot. Thank you.